Okay, last chapter in the course, chapter 7. Today's topic is continuous random variables. So, continuous random variables just says that you can represent the probability distribution by a table in a graph that relates each outcome of probability. So for discrete data, the one that can only take on certain values, often whole numbers, this is what it's going to look like. So when we flip a coin twice and we try to count the number of heads that we get. Okay, so we have three choices in a 2-coin flip. We can get 0, 1, or 2. The chance of getting 0 are 25%, the chance of getting 1 are 50%, and the chance of getting both heads are 25%. So when I take that to the graph, number of heads is 0, 1, 2, and the probability on this side, that's what it looks like in terms of graphical representation. So it's good to note that each rectangle has a width of only 1 unit. From 0 to 1, the space is 1 unit. And if you want to get the total areas, well, 1 times 0.25, 1 times 0.5, and 1 times 0.25, when you do that, it equals 1. And what does the area represent? Well, it represents the total probabilities being 100%, which we represent with the number 1. Okay? The other type of data that we can get is we can use something that's continuous. It's something that, like, for instance, time will do. And so the example is at a donut shop, the time required for a customer to eat a donut varies from 30 seconds to 3 minutes, with all times being equally likely. Because it's equally likely, it's a uniform distribution. Okay? And if I sketch the graph, on the bottom I have 30, 60, 90, 120, 150, 180 number of seconds. And because there's 6 boxes, I take the 100%, divide by 6, I get 17%, which I just represent as 0.17 as the probability. Okay, so what is the probability that the customer will eat a donut within 1 to 3 minutes? So if I were to shade in those 1 minute, minute and a half, 2, 2.5, 3 minutes, 5 out of the 6 boxes are shaded, which gives you a probability of 83%. Okay, so that's how that one works. Not too difficult, pretty simple. And a couple follow-up questions. How many values are possible for the required time to eat a donut? They're infinite because the time is continuous. I could eat the donut in 60.8359 seconds. Okay, so the continuous data, there's infinite possibilities. This is continuous data. And is it possible to determine the probability the customer will eat a donut in exactly 1 minute? Okay, so if I go back to the graph here, exactly 1 minute would be a dot. A dot has no width, has nothing to multiply it by. So in actual fact, the probability is 0. Because there's infinite possibilities, to get one exact precise value in infinite possibilities gives you a probability of 0. Okay. Then the next example, if you go to your textbook on page 325, there's just a frequency table. It just tells you the lifetime of these bulbs in days, and it just tallies them up. So all I did, whoops, that should just be one line. So I just tallied them up and I bring them to a histogram. So the histogram, lifetime in days and the frequency it occurred, I just get the different boxes. Okay, we've done that before. Okay, so that's a visual display. And then it asks you do a frequency polygon. So all you do is take the midpoints, 125, 135, 145, and then just join it with a nice line. And that's called a frequency polygon. Okay, so you're going to be asked to do that later. Okay, questions for today, 327, 1 to 3, 7, and 12. Good luck, and I'll be online if you have any questions.